All right, let's jump right in. Think of this as a bit of a chemical detective story. Our mystery for today? How in the world can we prove what's actually inside a pill you might have in your own home?
And the star of our show, our main suspect, is this guy right here, the humble aspirin tablet. Yeah, you've seen him a million times. Looks pretty unassuming, right? But believe it or not, it holds a pretty cool chemical puzzle.
So you look at the bottle, and the label makes a promise, right? It says, hey, there's a specific dose in here. But you know, in the world of science, a promise on a label just isn't enough. We need proof. So the big question is, how does a lab actually check? How do they make sure the dose you think you're taking is the dose that's really in that tablet? That's what we're going to figure out.
Okay, first things first. To crack this case, we've got to understand our suspect. And it turns out aspirin has, well, let's call it a tricky chemical personality. It doesn't make a direct investigation easy.
So let's get down to basics. What is aspirin, chemically speaking? Well, it's the common name for something called acetyl salicylic acid. Now, the key part of that name for us is acid. Specifically, it's a weak acid. And what do acids do? They react with bases. And that reaction, that's the breadcrumb trail we're going to follow.
But, of course, there's a catch. Here's our first plot twist. The main reaction we need to watch, a process called hydrolysis, is, well, it's super slow. It's so sluggish that trying to measure it directly is a real pain. You'd be sitting there forever waiting for it to finish. It's kind of like trying to time a race between two snails with a stopwatch. Just not going to work.
So, if the direct head-on approach is a no-go, what's a chemist to do? Well, you get clever. You use a little bit of chemical strategy. Instead of trying to chase the reaction, you basically jump ahead and wait for it at the finish line.
So we're at a fork in the road. Direct titration? Nope, off the table. It's just way too slow and clunky for aspirin. So our new tool of choice is this really elegant workaround called back titration. It's an indirect method, and it is perfect for this kind of problem.
Okay, so what in the world is back titration? It actually sounds more complicated than it is. The idea is brilliant in its simplicity. Instead of measuring the aspirin itself, you just overwhelm it. You dump in way more of a chemical that reacts with it, in this case, a base, than you could possibly need. Then, once all the aspirin has reacted, you just measure how much of that base you have left over. See? Clever.
Let's break it down into two simple steps. Step 1, we add a very precise known amount of a base called sodium hydroxide, or NaOH. This is our overwhelm chemical. It goes in and reacts with all the aspirin. Step 2, we figure out how much NaOH is left floating around by reacting it with a different chemical, hydrochloric acid, or HCl.
And here it is. This is the big aha moment. The whole entire technique just boils down to basic subtraction. Think about it. You know exactly how much base you put in at the start. You measure exactly how much is left at the end. The difference between those two numbers? That has to be the amount that got used up reacting with the aspirin. It's so beautifully simple.
All right, we've got our theory. We've got our clever plan. Now let's head into the lab, at least figuratively, and see how this all plays out in practice. How do you actually do this experiment?
Well, just like any good detective work, it all starts with the evidence. First, you have to weigh that tablet with incredible accuracy. Then, you get out a mortar and pestle and grind it down into a super fine powder. Why? To make sure every last bit of it can react. And finally, you have to transfer that powder into your flask so carefully. You can't lose even a speck.
Okay, now for the fun part, the chemistry. We add our excess sodium hydroxide. And remember that slow reaction we complained about? To give it a kickstart, we gently heat the whole mixture up. Once everything's reacted and cooled down, we add a couple drops of an indicator. That's what's going to give us our visual cue. And then, finally, we start the titration with the hydrochloric acid.
So how do we know when we're done? That indicator we added makes the solution a nice pink color as long as there's any of that leftover base around. As we drip in the acid, it neutralizes that base bit by bit. And then, poof! The very instant the last of the base is gone, the pink color just disappears. That's it. That's our endpoint. That's when we stop.
Okay, the lab work is done. We've got our measurements. Now it's time to put on our math hats for the final piece of the puzzle, the calculation. This is where we take all those numbers and translate them into the answer we've been looking for.
And the logic here follows our game plan perfectly. First up, we calculate the total amount of that base, the NaOH that we started with. Second, we use the results from our titration to figure out how much was left over. Third, we do that simple subtraction to find out how much of it actually reacted with the aspirin. And for the grand finale, we convert that amount into the actual weight of aspirin in milligrams.
This is a great way to see that core idea in action. So just as an example, let's say we started with 0.002500 moles of NaOH. Then, our titration experiment told us that we had 0.001320 moles left over. You do the math, and the difference, the amount that must have reacted with our aspirin, is 0.001180 moles. Simple as that.
So we take that final number, plug it into a conversion formula, and boom, we've got our answer. In this particular example, the math tells us the tablet had 106.3 milligrams of acetylsalicylic acid. The mystery is officially solved.
So, great, we figured out the amount in one single tablet. But why does any of this matter? What's the bigger picture? Well, this is way more than just a neat little lab experiment. This is a critical process, and it's one that actually helps keep us all safe.
Of course, just like in any investigation, things can go wrong. A good scientist always has to be on the lookout for potential errors. You could weigh something wrong or overshoot that endpoint by just one extra drop of acid. Maybe you don't heat it long enough. That's why having a super careful technique is absolutely crucial to get a result you can actually trust.
When you get right down to it, what we've just walked through is a real-world example of what they call pharmaceutical quality control. This is literally how drug companies make sure that every pill that comes off the line has the exact dose it's supposed to. It's a fundamental part of making sure our medicines are both safe and effective.
So there you have it. We've uncovered the really rigorous science that's hiding inside the process of checking a simple aspirin pill. Kind of makes you wonder, doesn't it? What other kinds of hidden, precise science are out there, working behind the scenes every single day to keep us all safe?